Let me just take one example, okay, just to make kind of matters a little more clear, and then we will go to the next level. Let me just look at one example. So just take this. This is a very simple example, but helps to make matters clear. So what it says is, let the 1D let a 1D unitary transform be given by, not the, let a 1D unitary transform be given by A is equal to 1 by root 2 1 minus 1. Have you seen this somewhere? Well, I mean, no, in terms of signal processing. Where do you want to go that far? What is this? Why do you want to go that far? Isn't this simply a DFT matrix of size 2, except for the scale factor? When you have Ej pi, what is that? E power Ej 2 pi by n kn, right? Kn. So k equal to 0, n equal to 0, and of course 1 by root n. K equal to 0, n equal to 0, so 1 by root 2 is anyway out. K equal to 0, n equal to 0, 1. K equal to 0, n equal to 1, 1. K equal to 1, n equal to 0, 1. K equal to 1, n equal to 1, Ej 2 pi by 2. So Ej pi is minus 1, right? So this is DFT. Let's not go Walsh Hadamard. We haven't even talked about it. So. Well, the only thing is, right, when they actually put this 1 by root n here, right, it's called a unitary DFT. Right, the normal MATLAB, I think it does not compute unitary. It skips that 1 by root n. Okay, but unitary we need because it's all about unitary. You don't want some alpha times identity, right? So A is equal to 1 by. So coming back to this problem, right, and let the image be given by. See, what I want you to notice, this is a 1D unitary transform. Okay, that A. This is not a basis image. Okay, A is still coming from. So all this A is right. As far as possible, I'll stick to the same sort of a notation. So when I write this A, it means it is the 1D unitary matrix. Okay, or the 1D unitary transform. And then what does it say? And let the image be given by. We don't want songs here. I think I can close that thing. Okay, 1, 2, 3, 4. So U is 1, 2, 3, 4. It's just a very simple example, right? So what is required is find the transformed image and the basis images. Okay, and of course, as far as we know, the basis images have to be independent of the image itself, right? They have to be independent of the input. Okay, so the basis images have to be constructed even otherwise independent of U. But then this transform, when we say what do we mean by the transformed image? Okay, one more thing I forgot to tell. Okay, yeah, right. So let me just put this as an aside. Now this equation, right, that you have, which is this, what is that? U, okay, or whatever, V. Well, I'm going to leave it as an exercise to you. So U is equal to, when I wrote double sum VKL, okay, A star KL, right? This is what I wrote. And V is equal to, okay, VKL in fact. VKL is equal to inner product U with A star KL. So, right, when I wrote this, okay, you can also see, for example, right, here you get every transform quotient, right? K comma L. So if you were to enter all those entries, just as your U has entries U00, U01, U10, U11, and so on, right, depending upon its size. Similarly, we will have the same size as U, because you are transforming the image. Just as you transform a 1D sequence of length n, you go to a transform domain wherein you have n coefficients. Similarly, here you have an n cross n image. If it is rectangular, it will be n cross n. Whatever. Let's just assume square for simplicity. So whatever is that size, right? Then we will also acquire the same size. So what this means is that your K and L, right, will have to go from 0 to, right, n minus 1. Okay, if U is n cross n. Okay, if U is n cross n image, then you will have to compute your VKL for all KL, right, going all the way from 0 to n minus 1. So if you put that up in a matrix form, you will get your VSM V00. Okay, where these are all right, they come from the VKL expression. So V01 all the way up to V0 n minus 1, and then you can come down, then Vn minus 1 0, Vn minus 1 1, all the way up to Vn minus 1 comma n minus 1. Okay, one way is to kind of find it out like this, but I'm going to leave it to you as an exercise to show that V is in fact, right, so this V, one way is to compute like this, okay, which is of course a matrix. Wanted to show that this matrix, when each of these entries is defined in this manner as the inner product of U and A star KL, write this back as in the form A U A transpose. So one is to look upon it as a summation, right, inner product and all of that. The other way to look upon it as simply a matrix operation now. Okay, so it's a small exercise. You can take some example and show this. Okay, just expand and then you'll be able to get this. But the nice thing about this is V, right, is really a 2D transform, right? Because if you see your image, it is actually a 2D image. Your 2D image is sitting here, correct? And you are actually asking for its transform. Okay. Now that transform can be obtained by actually pre-multiplying it with your 1D guy. So this A is not really a 2D transform. Okay, this A is the same A that you had for 1D. So this A is kind of pre-multiplying U, and then A transpose is kind of post-multiplying. There is no complex conjugate there. It is only A transpose. So A transpose gives you V. Okay. So the point is another way. Okay, but then right, this may not be still so kind of insightful. Right, I'm going to just leave it as an exercise to you to show that it is indeed true. You can just mathematically check this out, that the same VKLs, right? So if you check any entry here, suppose you write this as A00, A01, U00, all that, A transpose you write, you multiply each of those V00, V01 and all you will get, right, for every entry. You can check that will have the expression that you will get if you have to evaluate this particular this inner product. And you can see that A star KL, right, A star KL is not something that is dropped from the sky. Right, A star KL is in fact AK star AL star. AK star AL star transpose, and AK star AL star are themselves coming from A. Correct. So this relationship to A is kind of, this is one way to interpret it. Another way to look at it is getting indirectly embedded here. Because if you look at A star KL, you may wonder where is A sitting there. But then A is coming through these AKs, because A star KL is itself matrix that you get by taking AK star AL star transpose, and this AK star itself is coming as the column of the kth column of A Hermitian. Okay, so this A and right, so you can see that this should have entries of A, of course. When you try to write down VKL through the matrix expansion, you will get, of course, so you should be able to show this. This is nothing very this is simple. Now you can also write down what can you write U as then? If you can write it, the reason is, okay, some in some books, right, they like this form. In some books they like this form. In some books there is another form. Okay, and that form is the one that I like the most, because even now if you look at it, it looks like you have a 2D transform on the left, right, and then you have this U image which is getting sandwiched somewhere between two 1D transforms, right, and it is not clear why can't I write something like in the same form in which I write 1D. In 1D I write V is equal to A times U. Okay, but then when it comes to 2D, it looks like suddenly some kind of crazy things happen, and then right, it doesn't look like I can have this form. But then the truth is that you can have this form. Only thing is the interpretation of this A will have to change. The interpretation for a V will have to change. The interpretation of a U will have to change. Even though these still represent coefficients of the image, this still represents the image in some form, and then this should represent something that should have a relationship with the underlying 1DA. Okay, but it can't be the 1DA itself, but it should bear a relationship with the 1DA in some form. Okay, that form is the one that is most neat, and it's sort of it's like saying that it doesn't matter whether it will work in 1D, whether I work in 2D, whether I work in 3D, wherever I work, right, I can always write it up in this form, which is what we are all most familiar with, right? In 1D signal processing, this is the form that you're most familiar with. So why in 2D, right, we should have an expression like that. Nothing wrong with this. This is also true. But one still hopes that one would like to see something like the ones that we have seen for 1D. Okay, and once you have that, right, then that matrix becomes something special. This guy that sits there, and that and then what properties it has, and so on. Right, all those things begin to emerge. Okay, so at this point of time, I just want to say that okay. So yeah, so what is U then? So this is V, right? So U is A Hermitian. V, and then A. What? Can't be A, no? Has to be something. A star? Is it not? A Hermitian, A is identity, no? So A star transpose A is I. You take star, take star. So what do you get? A transpose A star is I star is I. So A transpose inverse is, what do you need? You needed A transpose inverse, no? Is A star. Okay, so okay, so now the point is this, right? So we want to find this. Now I'm going to arrive at this transformed image in various ways. Okay, so this is the most simplest thing, right? Would be to simply do this V is equal to, because transformed image is what your V, right? You're trying to transform it. So the simplest way would be A is equal to V is equal to A U A transpose, where A is this 1D guy. This is not really a 2D basis image, but that is the 1D unitary transform. I'll simply pre-multiply, post-multiply, and okay, let's not do it here. Okay, just leave it to you to show that this is 5. Okay, I have the answer here, -1, -2, 0. Okay, if you solve this, okay, what you'll get is this. Now, so the point is, right, some people like to see it as a complete matrix operation, the whole transformation, and therefore for them, right, doing something like this looks elegant. So 5 minus 1, so this is V00, this is V01, this is V10, this is V11. Okay, where each of these VKLs is that guy. Correct. So we can either say that, okay, that's our V, but then, right, we would also like to show that all these things also hold, whatever we wrote here, right, we would want to show that all those things also hold. So to show that, okay, now suppose we go back. Now if I want to solve this kind of inner product, right, then I need A star KL, no? I need all the 4 of them, A star 0, 0, everything I need, right? So suppose I ask what is your A, this is an Hermitian, but then that will mean that I should first take this A, compute A is a Hermitian, but in this case, right, it doesn't matter. It's real, and then it's also symmetric, so it is simply 1, 1, 1 minus 1, but this need not be true in general. Okay, need not be equal to A, correct, in general. This is a very, very simple case. So then what is your A star, whatever A0 star, that is 1 by root 2, 1 by root 2. Okay, what is your A1 star? 1 by root 2 minus 1 by root 2. Okay, and then, right, if you start looking at what is my A star 0, 0 then, okay, because I need each one of those here, okay, because I need KL going from 0 to 1, right? So A star 0, 0 is then 1 by root 2. Okay, so what will you get? 1 by root 2 into 1 by root 2, which is 1 by 2, right? 1 by root 2 into 1 by root 2, which is 1 by 2, 1 by 2, 1 by 2. It's okay, no? So it's like this way multiplying with itself, 1 by root 2, 1 by root 2. Then what about A star 0, 1? Okay, so 0, 0, 1 will be this with this. Okay, so this is like, what will you get? A star 0, 1, 1 by 2. So this is like this guy. So A0 star 1 by root 2, 1 by root 2, then 1 by root 2 minus 1 by root 2. So what will you get? 1 by 2 minus 1 by 2, 1 by 2 minus 1 by 2. Then what about your A star 1, 0? So 1, 0 is 1 by root 2 minus 1 by root 2, then 1 by root 2, 1 by root 2. get 1 by 2, 1 by 2, minus 1 by 2, minus 1 by 2. Then finally A star 1, 1. So that is 1 by root 2 minus 1 by root 2 into 1 by root 2 minus 1 by root 2. If you do this, 1 by 2 minus 1 by 2 minus 1 by 2, 1 by 2. Correct? Of course, you can all check that if you were to take the inner product, that now we have already shown. Okay, we don't want to go through all that. Now, the point is, suppose I'm interested in V00. Right, so V00 is what? Inner product U with A star 0, 0. Now, in this case, everything is real, therefore, there's no need to take any. So, U is what? 1, 2, 3, 4. No. So, if you look at A star 0, 0, A star 0 is sitting here. Right? And our U is there. Look at this guy. So, this will be 1 into, there is your A star 0. So, 1 into 1 by 2 plus 2 into 1 by 2, which is 1, plus 3 by 2 plus 4 by 2, which is 2. Right? So, what is this? 1 and a half, 3 plus 2, 5. Right? Which is what you got here. No? Right? Which is what you got here as V00. Okay. It should, of course, match. Right? So, there should not be any surprises there. So, V01 is inner product U with A star 0, 1. So, look at A star 0, 1 is here. So, this will be 1 into 1 by 2 plus 2 into minus 1 by 2 is minus 1 plus 3 into 1 by 2. So, it is 3 by 2. First 4 into, so it is minus 2. So, what do you get? Minus half, 1 and a half, 1 minus 2 is minus 1. Right? Okay. So, that's the same as what you had here for V01. Okay, then come to V10. 10 is inner product U with A star 10. So 1 into 1 by 2, that's 1 by 2 plus 1 minus 3 by 2 minus 4 by 2 is minus 2. So minus 2, right? These two cancel off. Then V11. So as you can see, right, this is the same as whatever you got through the direct sort of a matrix multiplication. U with A star 1, 1 is here. So 1 by 2 minus 1 minus 3 by 2 plus 2. So half minus half is minus half. Minus half minus 1 and a half is minus 2 plus 2 is 0. Right? So that is again the same as what you had here. Okay. So there's one way to check that all your VKLs, right? Whether you come through AUA transpose or whether you come through come through an expression like that where you take the inner product, construct the basis images, okay, which is actually a 2D basis now. You can come either via a 2D basis image and then compute your coefficients, or you can still use the 1D unitary transform itself, do the matrix multiplication and get there. And then you can of course clearly show that you can reconstruct U, right? So if you try to get this expression now, so V00, okay, which is like what is it, 5 times. So what will it be like? So if I try to reconstruct, right? So 5 into A star KL. Can somebody tell that? So 5 into A star is 5 by, what will that be? 2.5 minus plus half. Yeah. If you can tell me 2.5 minus 2.5, what was it? 2.5, 2.5, yeah? What was it? 5 times A star 0, 0 is, what was the last one? All are 2.5? No, minus 2.5 is there, no? Oh, okay, all are 2. Oh, I am looking at the wrong one. Yes, all are 2.5. Correct. I am looking at plus. Okay, V star 0, 1 was how much? Minus 1. So that we need to multiply with A star 0, 1. So that will be minus half. What is it? Minus half plus half. And then minus half. Minus half plus half. Then third guy is what? Some minus 2 or something we saw. No? So minus 2 multiplying A star 1, 0. What is that? Minus 1 minus 1 plus 1 1, and then the final one is anyway 0, right, because that quotient itself is 0. So if you add all this, 2.5 minus 0.5 is 2, minus 1 is 1, 2.5 plus 0.5 is 3, minus 1 is 2, 2.5 minus 0.5 2, plus 1 is 3, 3 plus 1 is 4, right? So this is equal to u. Okay, this is only a small example to show that, right, one can kind of see we are around, okay, whichever way we want. We can either come via inner product, or we can come via matrix, or we can come via, right, the whichever formulation we want. But now the point is, right, we'd like to kind of take this forward, right, and look for a formulation, right, where even in 2D, okay, we would like to be able to write something like V is equal to something multiplying U, where this can be interpreted as a 2D transform. Okay, that form, right, we would like to kind of right, we'd like to see. Okay, in order to see that, okay, before we can see that, okay, we will have to look at what is really called a Kronecker product. Okay, now before that, right, I still have to write a few more things, okay, before we get there. No. I think prior to that, right, there's still some more work that needs to be done. Okay. Now I'm going to make a claim. Okay. I want you to check this out. Okay. This is again yet another form. Okay. If time permits, we can do it today. No? So claim is this. The same VKL, right, which we said is inner product of U with A star KL. That was one way we wrote it. Or we said, just have the whole matrix V coming out as AU A transpose. Yet another form for this VKL is as double sum AMN. Okay, and note that these small a's are again the same entries of the matrix A, of the 1D guy. Okay, these are the same a's. Okay, so I'm not changing anything along the way, so that we can always map back to what we started off with. So no, this is not AMN. This has to be AKM, K comma M, Q of M comma N, and then A of L comma N, and then this sum runs over M comma N, and then K and L, and then it's over 0 to N minus 1. Okay, now right, so the point is, okay, something like ideally, right, what you would have thought, right, it might look like is UMN, which is my image, then multiplying a 2D transform that is of the form maybe K comma M comma L comma N. Okay, now most transforms, okay, that we encounter, that the ones that you are familiar with, are all transforms wherein this guy is actually separable. This guy separates as A, so it splits as AKM and into AL. And for example, if you take a Fourier transform, okay, in 1D it is e raised to minus j2 pi by n kn. Look at a 2D form, it will be e power minus j2 pi by n nk plus nl. So it kind of splits. So you have, so not only this, I mean, your DCT, your DST, every one of these, right? There are some which are not separable like this. Okay, it's not true that everything is separable, but most of the transforms that you use in your daily life, right? And also, right, there is also a reason for it. Okay, why we like such separable transforms is because whatever sort of equipment you have already developed, whatever tools you have developed for 1D, okay, you can all those we can actually directly use for doing 2D. For example, if you look at a 2D Fourier transform, if you want to calculate, you might say it's an image, and therefore computing a 2D DFT looks like a lot of work, right? Because you will have like n square quotients to compute. But then you know that there is a fast Fourier transform in 1D. Right? So you might want to ask, can I sort of employ that 1D FFT, which is already so quick, right? Can I kind of use that to do a computation of my 2D Fourier transform? So all that, right, is possible provided this kind of a separability notion is there. And in fact, when most of the transforms that you would come across are of the separable type. Okay, and these separable transforms. In fact, when I did A star K into A star L transpose, I assumed that separability already there. Okay, that is because see, in books, right, when they write this, okay, the separability notion, okay, is made kind of say explicit when they kind of write the summation, because ideally you would have thought that it might look something like that. Okay, now instead of, but then the point is, right, if you write like this and move on, right, there is so much of matrix structure that lies underneath, right, that you will miss. Okay, you won't see any of that. Okay, if I had simply introduced DFT as UMN e power minus j2 by n km plus nl and said that anyway, right, this is a separable transform and therefore, right, that is how a 2D basis image will look like, then you will actually miss the point that irrespective of which transform you're looking at, provided, right, all these transforms are basically unitary and separable, then there is a nice structure, right, which binds all of them, which binds 1D to actually 2D. And the same vehicle, right, that you use to go from 1D to 2D, it becomes very obvious that if you wanted tomorrow, right, if you wanted to do a 3D processing, right, let's say, instead of just image, you have a complete, this one, a video, which is kind of varying with time. Now, if you say, if I wanted to do, a 3D DFT, now you won't have to wonder, as to what should I do next, what kind of basis images will I get, and so on, because this vehicle is so structured that it is automatic. Why 3D? Right? If you wanted to go to 4D, 5D, right? Doesn't really matter. So that structure you tend to miss. Okay, which is, but then all these forms are correct. Okay, it's not to say that one form, nothing like any form is inferior. But I'm just saying that going through a matrix sort of operation, right, throws up so many things, okay, which we don't see, which we don't see otherwise. We'll simply miss all of that and think that and even the diagonalization capability of certain matrices and all, none of that we can see. It will all look like each one is a standalone. A DFT will have this summation, a DCT will have that summation. Whereas if you just take some A, right, and don't really worry about what is a DFT or DCT or Walsh or somebody said, right, Walsh, Hadamard, right, we don't really care about any of that. We know that all of them are unitary, all of them are separable, and if you can develop a common framework which allows you to seamlessly go, right, you shouldn't take an effort to kind of go there. It should be a seamless thing. If you can go seamlessly from 1D to 2D, then it automatically means that from 2D to 3D should be another seamless task, right? And that is what we are hoping to do. Okay, but in the process, we should also be aware that if you see books, right, they might have expressions like this, and you should not wonder what is this, right? I never spoke about this. Okay, so I'm saying that all these mean the same thing. They're all is equivalent. Each one, if you look at it as a matrix vector operation, it may look, it may take a certain form. If you look at it as a summation, it may take a certain form. But I always like to go back to the kind of matrix form, because that is where the entire structure is embedded. Okay, and these are kind of other ways of interpreting the same equation.